Bismillahir Rahmanir Rahim. In the name of Allah, the most beneficent and merciful. Dear student, Assalamu alaikum. We are back with our ninth lecture about single crystal X-ray diffraction, in which we have studied different techniques using different kind of sources like X-rays, neutron, electron, and this is the third technique that we are studying in this lecture. This is Scanning Electron Microscopy SEM. Our course code is CHEM 5134, and this third chapter is about X-ray diffraction technique. My name is Dr. Rana Farhat Mehmood. So here we will start about how a scanning electron microscope works. The main SEM components include source of electrons, column down which electron travel with electromagnetic lenses, electron detectors, sample chambers. These are the main components of scanning electron microscopy. So computer and display to view the image is also required, which is combined with these sources. Electrons are produced at the top of the column and accelerated down and pass through a combination of the lenses in the aperture to produce a focus beam of electron which hit the surface of the sample. The sample is mounted the sample is mounted the sample is mounted on a stage in the chamber area, and unless the microscope is designed to operate at low vacuum, both the column and the chamber are evacuated by a combination of pumps. The level of the vacuum will depend on the design of the microscope. Here is a schematic diagram of SIM scanning electron microscope, which starts with the electron gun which produces electron beams, and then there are condensers lens located in the path of the electron beams, and then a spray aperture is also present after the condenser lens. Then again second condenser lens is installed, and then after that deflection coils, final lens aperture, and backscatter electron detector is present in the pathway of the electron beam. After passing all these components of the SEM, the electron beam incident on the sample and then diffracted from the sample and is recorded by the X-ray recorder. So there is a secondary electron detector which detects the scattering of the electrons after the incident of the sample, and then here is a vacuum pump that we have discussed in the previous slide, that are used to evacuate the chambers. The position of the electron beam on the sample is controlled by a scan coil situated above the objective lens. These coils allow the beam to be scanned over the surface of the sample. This beam restraint or scanning, as the name of the microscope suggests, enables information about the defined area on the sample to be collected. As a result of the electron-sample interaction, number of signals are produced. These signals are then detected by the appropriate detector. Sample electron interaction. The sample electron interaction can be studied in a way that scanning electron microscope produce images by the scanning of the sample with the high energy beam of electrons. As the electron interact with the sample, they produce secondary electrons and backscattered electrons and the characteristic X-rays. These signals are collected by one or more detectors to form images which are then displayed on the computer screen. When the electron beam hits the surface of the sample, it penetrates the sample to a depth of a few microns, depending on the accelerating voltage and the density of the sample. Many signals like secondary electrons and X-rays are produced as a result of this interaction inside the sample. So there is a schematic diagram of electron beam interaction with the sample in which agar electron, secondary electron and backscattered electrons are located, and the characteristic X-rays are also shown, and continuum X-rays and fluorescent X-rays are also can be seen here in this diagram. Dear student, the maximum resolution obtained in a scanning electron microscope depends on multiple factors like the electron spot size and the interaction volume of the electron beam with the sample. While it cannot provide atomic resolution, some scanning electron microscopes can achieve resolution below 1 nanometer. Typically, modern full-sized scanning electron microscopes provide resolution between 1 to 20 nanometer, whereas desktop system can provide a resolution of 20 nanometer or more. Here we are going to discuss about how is the path of electron controlled. In a similar way to optical microscopes, lenses are used to control the path of the electrons because the electrons cannot pass through the glass. The lenses that are used here are electromagnetic. That's why they simply consist of coil of wires inside metal pole pieces. And when the current passes through the coils, a magnetic field is generated. As a result, electrons are very sensitive to magnetic field and their path inside the microscope column can be controlled by these electromagnetic lenses. Simply by adjusting the current that is applied to them, generally two types of electromagnetic lens are used. Number one is the condenser lens, is the first lens that electrons meet at the travel towards the sample. This lens converges the beam before the electron beam come open again, and it is converted once more by the objective lens before hitting the sample. The condenser lens defines the size of the electron beam, which defines the resolution. while the main role of the objective lens is to focus the beam onto the sample. So there are two kind of lenses. One is condenser lens and other is objective lens. And what does the condenser lens do? The condenser lens defines the size of the electron beam, while the main role of the objective lens is to focus the beam on the sample. The scanning electron microscope's lens system also contain the scanning coils, which are used to raster the beam onto the sample. In many cases, apertures are combined with the lens in order to control the size of the beam. These main components of a typical scanning electron microscope instrument are shown in the following figure. Figure is the schematic representation of the basic scanning electron microscope components, in which there are different components of the microscope are shown, starting from the electron source, then anode, condenser lens, scan coils, objective lens, and the sample, and after that scanning electron detector. Now we will see that what kind of electrons are there. The interaction of electron with the sample can result in generation of many different type of electrons, photons, or irradiations. In the case of scanning electron microscope, the two type of electrons used for imaging are the backscattered BSE electrons and the secondary electrons. The backscattered electrons belong to the primary electrons beam and are reflected back after elastic interaction between the beam and the sample. While on other hand, secondary electrons originate from the atom of the sample, and they are as a result of inelastic interaction between the electron beam and the sample. Backward scattered electrons come from deeper region of the sample, while secondary electrons originate from surface regions. Therefore, backscattered electron and secondary electron carry different types of informations, while backscattered electron image show high sensitivity to differences in atomic number. The higher the atomic number, the brighter the material appears in the image. Here is a figure which is showing different type of signal used by the scanning electron microscope and the area from which they originate. Scanning electron microscope, in which secondary electron imaging can provide more detailed surface information, something you can see in the following figure. In many microscopes, detection of the X-rays which are generated from the electron matter interaction is also widely used to perform elemental analysis of the sample. Every material produces X-rays that have a specific energy. X-rays are the material fingerprints. So, by detecting the energies of the X-rays that come out of a sample with an unknown composition, it is possible to identify all the different elements that it contains. Figure A shows the backscattered electron and B secondary electron image of the iron oxide particles. Mechanism of the emission of secondary electron, backscattered electron, and characteristic X-rays from atom of the sample can be seen in these figures. Electron diffraction technique. The electron diffraction ED techniques can be divided by the energy used, that may be high energy or low energy, the geometry, the transmission or reflection, and the type of the beam, parallel or convergent. So on these factors, the electron diffraction techniques depends on. ED mean electron diffraction. HEED is abbreviated as high energy electron diffraction. LEED, low energy electron diffraction. THEED, transmission high energy diffraction. And RHEED stands for reflection high energy electron diffraction. Whereas SAED is stand for selected area electron diffraction, and NED stand for nano area electron diffractions. CBED can be stated as convergent beam electron diffraction, and LACBED is stated as large angle convergent beam electron diffraction. So these are the abbreviation that we have studied in the previous slide, and here these are shown that how they are interconnected with one another. Low energy electron diffraction, LEED. A beam of electron of a well-defined low energy, typically in the range of 20 to 200 electron volt, is incident normally on the sample. The diffracted electron can be observed by the fluorescent screen after energy filtering grids, which selects only the electron with the same kinetic energy as the primary electrons. Here we can see that electron gun provides the electron beam, and that electron beam strikes the crystal sample, and after striking these X-ray electron beam are scattered and are recorded on the screen in the form of grids. Remember that this is order of the crystal lattice parameter. Reflection high energy electron diffraction, RHEED. Here we can see that electrons with 5 to 100 kilo electron volt are directed toward the sample at very near QI angle 90 degree and keeps very long path length high energy electron in near surface region. To increase surface sensitivity and also to have a K component comparable with the G of the crystal. Forward diffracted electrons strike phosphoro screen grid used to repel secondary and inelastically scattered electrons, and 50 kilo electron volt electron have 1 is 0.055 angstrom and K is equal to 114 angstrom inverse. So what is electron diffraction pattern? For single crystal actually consists of atoms arranged in an orderly lattice. Some types of crystal lattice are simple cubic, face center cubic, and body centered cubic. In general, single crystals with different crystal structures will cleave into their own characteristic geometry. For example, crystals of quartz, calcite, or carbon in the form of diamond. Single crystals are the most ordered of the three structures. An electron beam passing through a single crystal will produce a pattern of spots, and from the diffraction spots one can determine the type of the crystal structure, that it may be face centered cubic or body centered cubic. And the lattice parameter, that is the distance between adjacent planes, and that plane may be in the form of 100 Miller indices. Also, the orientation of the single crystal can be determined by using electron diffraction pattern. Here in this slide, we will discuss that X-ray striking a single crystal will produce diffraction spots in a sphere around the crystal. Each diffraction spots correspond to a single HKL Miller indices. The distribution of the diffraction spots is dependent on the crystal structure and the orientation of the crystal in the diffractometer. The diffracting condition is best illustrated with the evolved sphere in the reciprocal space. And the diffraction spots are sometimes called reflection. Three cheers are for sloppy terminology. So in the figure we can see different kind of diffraction pattern that can be recorded on the film, and by these diffraction pattern we can find out the HKL values that depict the uh, Miller indices, and these Miller indices are the planes of the crystal system. For polycrystalline material made up of many tiny signal crystals, most common metal material, copper pipes, nickel coins, stainless steel forks are polycrystalline. The single crystal grain in the polycrystal will have a random distribution of all the possible orientations. Ground up powder sample appears polycrystalline. and a polycrystal is not as ordered as single crystal. An electron beam passing through a polycrystal will produce a diffraction pattern equivalent to that produced by the beam passing through series of single crystals of the various orientation. The diffraction pattern will therefore look like a superposition of single crystal spot pattern and a series of concentric rings resulting from many spots very close to each other at various rotations around the center beam spot. From the diffraction rings, one can also determine the type of crystal structure and the lattice parameters. The orientation of a polycrystal cannot be determined. Polycrystalline material are made up of tiny single crystals. They are not in the ordered form. Single crystals grain in the polycrystal have a random distribution of all possible orientation. That's why diffraction pattern will therefore look like a superposition of the single crystal spots pattern and a series of concentric ring resulting from many spots very close to each other at various rotation around the central spots. From the diffraction ring, type of crystal structure and the lattice parameter can be determined. One cannot determine the orientation of a polycrystal since there is no single orientation and flipping or turning the polycrystal will yield the same ring pattern. Dear student, that's all for the today's lecture number 3.9 of our third chapters about single crystal X-ray diffraction, and the remaining portion of this scanning electron microscopy will be discussed in the next lecture 3.10, and that most probably will be our last chapter about single crystal XRD. Till then, Allah Hafiz. Thank you very much.